In this lesson, we'll define the exponential function and have a look at its graph. We have a table of values for the exponential function y equals 2 to the power of x. 2 to the negative 3 is 1 over 2 to the 3, which is 1/8. 2 to the negative 2 is a quarter. 2 to the negative 1 is 1/2, and so on down the table. Plotting those points, we get this graph. For example, here where x is -3, y is 1/8. Here we have x is -1, y was 1/2. The y-intercept, x is 0, y is 1. We can join those points together now, and we'll get the complete exponential graph of y equals 2 to the power of x. The exponential function will have the basic form of b to the power of x, where b is the base, which is some number bigger than 1. The x-axis is an asymptote to this graph, and the function is increasing. In an investigation, we see what happens when we change the base of that function. We can, of course, apply transformations to this function to dilate it and translate it. So we can change the equation to this, where the a is dilating in the y direction, the n is your compression factor in the x direction. Let's move d units to the right and c units up. So that means our asymptote is also moved c units upwards, so it'll become y equals c instead of y equals 0. To change our function to a decreasing function, then we need to make the transformation that will reflect the graph in the y-axis. That means that we need the n to be negative. So for example, a b to the negative x here will give us a decreasing function, and the b once again will have to be bigger than 1. So here we've changed our graph to a decreasing function. Geometric progression occurs when each term of a sequence is obtained by multiplying the previous term by a common ratio. We saw an example of that with the paper folding, where each time we folded the paper, we doubled the number of layers. The nth term of a geometric progression is given by Tn for nth term is equal to the starting number a multiplied by the common ratio n minus 1 times, where n is the number of terms. So the first term is a, you don't multiply that by the ratio. The second term is a times r, so the second term will be multiplied by r once. Compound interest is another example of a geometric progression. We have a principal amount P that's invested at an annual rate of R%, and interest is paid n times a year. Then the value of the investment is given by the formula V is equal to P times 1 plus the rate of interest divided by 100 over n to the power of n times t. Here's a compound interest example. We have $1,000 invested at a compound rate of 12% per annum. The interest is paid monthly. What's the value of the investment after 3 years? So we use the formula we established in the last slide, where our principal is 1,000, our rate of interest is 12%, and the number of installments per year is 12. We put all those numbers into our formula. We can simplify that down and then use our calculator to work out our answer. So we saw that the exponential function has the form of f of x equals b to the power of x, where the b is bigger than 1. The x-axis is an asymptote to this graph, and the function is increasing. We can change it to a decreasing function by putting a negative before the x. So we'll have f of x is equal to b to the negative x will make it a decreasing function.